again, thanks to Claudio and the organizing committee for this invitation. And I would like to give you an overview of why I think it's absolutely essential that we be able to quantify GFR. So I'm going to talk a lot about why, a little about how and when. If I can get to full screen here. Okay, so again, I have a conflict. We're trying to develop this technology. We're in phase 2 studies, and I will, again, say that as we go through. So why is a measured GFR at the point of care needed? Well, first of all, GFR is a physiologic process. It's not a surrogate of anything. It is an absolute physiologic process that's a measure of global kidney function. As you know, serum creatinine and eGFR are surrogate markers, and they're unreliable due to insensitivity, altered release of creatinine, muscle wasting in 90 days, many, many reasons that they are unreliable in many patients. Determination of GFR would allow for rapid diagnosis and stratification instantaneously of how severe the kidney injury is. It would also allow for rapid determination of response to therapy, very important in differentiating prerenal from ATN. And it would allow us to quantify loss of functional recovery from an acute event sometime in the future, which is an endpoint for determining a therapy in AKI. So I think the therapeutic translation requires quantitation of GFR because of the endpoints now mandated on this side of the pond and on our side of the pond. And I'll make my point here. This was a retrospective analysis done by John Prowl. And I think it's critical to really look at these data, because what he did was he went into 700 ICU patients that were in the ICU for 5 days or more, so sick ICU patients. This wasn't rapid recovery. And they looked at their serum creatinine, and he divided these patients using the Akin phenomenon into no AKI, AKI 1, 2, and 3. So no AKI, it's very interesting that their discharge, which is the third bar over from the left, creatinine is less than their admission, implying that they had improved their kidney function by being in the hospital in the ICU. We know that doesn't happen. And even at 90 days or later, they still had a lower serum creatinine. They didn't have AKI. If you look at AKI 1, same story, okay? Discharge creatinine less than entrance creatinine, and after 90 days, still less. Well, let's go to AKI 2. Same story. So let's go all the way to AKI 3, and 40% of these patients required dialysis or some form of renal replacement therapy. And you can see that their peak serum creatinine was 5 plus or minus a wide standard deviation. But at discharge, it was down to below baseline. They could have come in with a little AKI. And at 90 days, it was still 90 days or greater, still less than that. This means in this population that started out with relatively normal GFR, you will never have a therapeutic agent because the endpoints are death, dialysis, and an increase in serum creatinine or decrease in eGFR. Okay? So you could never have a positive therapeutic trial in this population. So why don't we determine GFR? We know we have gold standard techniques, yet the sampling techniques that we have to use for inulin, iohexol, urinary creatinine, iothalamate clearances all have complications. Number one, they're single compartment tests in general. They take 6 hours to administer the test, and most of those, the inulin, iohexol, and iothalamate, then take a day or two to get the results back from your lab. Obviously, in a hospitalized patient, it's just way too long. They're expensive, they're time-consuming, they're cumbersome, they're just not practical. And given the 6 hours of timing, the GFR could even change while you're doing the study. And people do use creatinine clearance. I think it's about what we have, but it's well known, especially during sepsis, that creatinine release is not constant and therefore not reliable. Now, we've heard a lot in the last 10 years about AKI leading to CKD, but I want to point out the reference to you here. This was a 1956 paper by Merrill and colleague in the New England Journal where they looked at 16 30-year-olds that were previously absolutely healthy from a cardiovascular and total body fashion that had oligoanuric AKI. Now, in 1956, we didn't have dialysis, and they studied them in follow-up. You can see them months after oligoanuria, and you can see what their inulin clearance is in these patients. So we knew in 1956 that AKI leads to CKD, right? This is not a new phenomenon. And so I went back to this paper, and I knew I would find the serum creatinines and that the GFRs wouldn't match with serum creatinines, but in 1956 we didn't measure serum creatinine, we measured inulin clearances. Okay, another point I'll make with a preclinical study, if you just focus on the blue lines here, this is a rat study. You clamp the kidney, you give it acute kidney injury, and you can see in the first upper left-hand panel, serum creatinine goes from about 0.4 up to 2, and by day 7, it's back down to nearly 0.4 again. And we call this complete recovery in the rat model. Look at the GFR measured with a creatinine clearance, either in the panel to the right or the panel below, and you'll see that at 7 days, the GFR is 1/4 of what it started out. And at 14 days, it's a half. And at 21 days, it's 3/4. And finally, at 28 days, it's back to where it belongs. And you're going, how can a GFR be that low when the serum creatinine is already back to baseline? These animals lose 20% of their weight in the first 3 days after acute kidney injury, just like our patients lose a high percentage of their muscle mass when they're sitting in the ICU, very sick. So that muscle mass is critical when you're looking at a serum creatinine. And we all know that they lose it. And if we're going to study this at 90 days in a sick population that didn't have a normal GFR to start with, and we can't account for it, I'm not sure how we're going to get positive. Now, this next point, you know very well that this is an exponential curve looking at serum creatinine and GFR, and that you can have a large change in GFR with a very small change in serum creatinine, and so one finds it very difficult. This is an insensitive portion of the curve, and this is why your estimating equations work far better if your GFR is below 60. But it's even worse than that, and that's what has been talked about by numerous people at this meeting, and that's the renal reserve. Now, when you develop AKI, do you lose renal reserve first, or do you go into your baseline GFR? We don't know that, but many of us would pretend that you lose this renal reserve. So before you get to a point where you can detect a serum creatinine change, you could have lost 2/3 of your total kidney function. And you wonder why it takes 2 days to see a bump in your serum creatinine? You wonder why they call it subclinical AKI when you have biomarker sensitivity and not creatinine, and they say that there's no functional change. There's no functional change with a insensitive marker. It's not that there's no functional change. We just have not developed the technology to measure it. So to make this point even more, let's take a look and use a standard CKD epi equation on a 70-kilo or 40-year-old male and say, okay, if we're going to give them acute kidney injury by the diagnosis of a 0.3 milligram change in serum creatinine, how much GFR do they have to lose if they start with a baseline serum creatinine of 1? Oh, well, they have to lose 32 mils to get 0.3. But now let's go to that same patient and say their baseline serum creatinine is 2. Well, they have to lose 7 mils to get that same diagnosis. So one of the reasons that CKD patients are more prone to AKI is that they can lose less GFR and still have a positive diagnosis. If you get to a serum creatinine of 3, you lose 3 mils of GFR, and the diagnosis of AKI is made by the 0.3 change. So think about that when you see your CKD patients being very fragile in this. And what this has caused us to do is to take our AKI studies in our post-cardiovascular patients and move them so that they all start with creatinines in the 2 to 3 range, right? That's where we do it. We don't do it in normal patients because serum creatinine is not sensitive, and that's one of the endpoints. So we move all of our studies so that we can have a high number of events in the numerator to patients where a very small change in GFR leads to a positive diagnosis. So we're shooting to try and salvage 5 to 7 mils of GFR in these patients that start between 2 and 3, instead of shooting for 40 when the patients start with a normal serum creatinine, because we can't measure GFR. Okay, so let's go to glomerular filtration rate. It varies throughout the day. 24-hour urine measures an average of the GFR throughout the day. Renal reserve is that portion of the GFR that can be stimulated above baseline. And the ways to stimulate that, as you heard here, is a protein meal. It's also an amino acid fusion, dopamine infusion, or glucagon infusion, okay? I personally like the amino acid infusion because you can get a standard operating procedure and repeat it very nicely each time, and you don't have to worry about gastric emptying, et cetera, et cetera. When we lose GFR from injury, do we first lose renal reserve or baseline? Do we lose them proportionately? We don't know the answer. And therefore, what GFR should we quantify? Should we quantify total stimulated GFR as the most sensitive measure of what the kidney has to offer? Think about the heart, okay? We're always following the cardiologist. If you see an ejection fraction of 50%, does that mean that they have a normal heart? That they have a normal ejection fraction? No. If you really want to evaluate cardiac function, you do some type of stress test, an exercise test, and then you can see what kind of heart they have. You can do the same with the kidney. So this is what GFR in cartoon fashion looks like throughout the day. If you eat protein, and especially animal protein, every time you have a meal it goes up, and your 24-hour clearance gives you the average of that, okay? Again, this is baseline, this is close to maximally stimulated GFR, and what's going to be the most sensitive, what should be measuring. Obviously, if you measure a fasting versus a GFR after someone's eaten, your baseline GFR is going to be different, right? So we have to be careful of that. So what happens to renal reserve? Well, this was a paper done by Juan Bosch back in 1984. He was mentioned by Mink as a person who specialized in studying GFR at that time. And on the y-axis, you can see the percent rise in GFR, and on the x-axis, you can see the baseline GFR. And what you see is the rise as a percent in GFR is independent of where you start. You have a patient out here who is obviously hyperfiltrating at a very high GFR that has no rise in GFR when stimulated, okay? You have patients in here that have a very low GFR who have a lot of reserve. Okay? Obviously, if you have a lot of reserve and you use that up first, you're going to be a non-progressing CKD patient. Okay? Whereas a patient who has no renal reserve, such as a hyperfiltering diabetic who now enters the decline phase, is going to be a progressive CKD patient. We need to be able to evaluate renal reserve. And just to make one last point here, to drive it home, let's look at what happens to kidney donors when they donate a kidney. This was a very nice study, not done by nephrologists, done by transplant surgeons, where they looked at baseline serum creatinine of normal donors with normal serum creatinines, 0.96, and they stimulated them using glucagon dopamine infusion, and they got a 30 mil increase in their renal reserve. Then they took a kidney, and they looked at the remaining kidney a few weeks later. Now, that remaining kidney, they couldn't stimulate it because it was already using all of its renal reserve. So if you look at the GFR here, it's 113, and here it's 72, and so they would say you lost 41 mils. No, you didn't. You lost 71 because you went from 143 to 72 because this is using all of its renal reserve to generate that 72. So you didn't lose 41, you lost 71 mils of kidney function because you lost half of your kidney function in this patient. And renal reserve hides this loss. Okay, so now, how are we going to measure this? Well, there's been a lot of work in the last few years to try and develop a commercially available, easy-to-use, bedside-type diagnostic in this area. And what's winning out is a fluorescent technique done with either a non-invasive external detector you'll hear about with the next speaker, or the type we use where we inject 2 fluorescent dextrans and measure both plasma volume and the clearance of one of the dextrans with 3 blood samples. But this just shows you some of the work going on in the field, and I think within 2 to 3 years you will have a commercially available technique that you can use in the bedside to do this with your patients. So let's look at a fluorescent single compartment GFR determination. The advantages, and you're going to hear more about this in the next speaker. It's straightforward. Multiple compounds can be used. It works by determining ECF fluorescence with an external detector, so it's put on the skin. And you can do continuous infusions, as I'll show you in a second, and follow what happens to that infused fluorescent marker dynamically. The challenge is this is a longer test because it's based on reading in the extracellular space. It yields a rate constant for GFR and not a true constant. That rate constant you multiply by an estimated plasma volume to give you your GFR. If plasma volume isn't what you estimate, your estimate's going to be off. You need a large amount of the compound to be infused, but as you'll hear, that's changed. They have come a long way with the fluorescence of the molecules they're studying. Requires normal sub-Q perfusion. Can we use this in an ICU where we have reduced sub-Q perfusion? And you have to worry about variability in skin thickness where you read this out and as you're reading it out. Now, this was a very nice paper up here in 2012 in KI where they said, well, now, instead of a bolus infusion, let's infuse this constantly and let's develop a transcutaneous device that will allow us to read it. And you can see their readout here, okay? And this is not in humans. This is, I believe, in rats. You see a very stable, constant level of extracellular fluorescence. Now, if your GFR goes up, this level fluorescence would go down. And if your GFR goes down, this would go up. And so here's the dynamic readout that potentially will be available in the future. Now let's look at a multiple compartment GFR determination. The advantages is it can go much faster because you're dependent upon plasma clearance, not ECF clearance. You can measure renal reserve with this because you can do an hour infusion and measure your stimulated GFR. The amount of the compound given is very, very small because it doesn't have to fill up the extravascular space. We use a second marker, and again, I'm in conflict here, I'll just tell you that. We use a second marker that is a true measure of plasma volume, whether it's up, down, or normal. And in our sick patients, it can be any place. Plasma volume, as I showed in the previous talk, can be followed dynamically, and gives you a GFR, not a rate constant. The challenges, invasive detection. We draw 3 blood samples to get this done, and intravascular probe needed for continuous study could be used with a triple lumen central optical catheter. We've chosen not to go that direction for financial reasons primarily. We can only go one direction. So this is what the tests look like. We inject a large red dextran, 150 kD. Remember, albumin is 70. Albumin leaks into the interstitium. 150 is going to be a lot less likely to leak. And a small green marker, which is an FITC labeled dextran in the 5 to 6 kD inulin size. The dextran is freely filtered across the glomerulus, the small one. The large one has a glomerular sieving coefficient of 0. These are the type of curves we generate. You can see here the indwelling optical probe curve for the small molecule being cleared, the large molecule being stable. You create a ratio of that. And just to show you what the blood samples look like, these are blood samples drawn along, and this is how they fit the curve. They fit it very, very nicely. This is a normal GFR in a dog. This is a very slow GFR, CKD GFR in a dog. You can see the difference between the fluorescent clearance of the small molecule here and here. And this is the correlation with iohexol clearances that we did early. Now, another advantage of this is you can, if you did it dynamically, you could tell the computer to figure out when the GFR was stable, and you could stop the test then. Again, we're using blood samples and not that now. So, indwelling probe versus blood samples in phase 1 study done in Germany in a CRO. Peripheral vasoconstriction and appropriate vein size was a limiting factor in normals, let alone going into sick patients. So at that point in time, we finished that study, but we went then on to blood samples. And again, you can see how the blood samples match with what the indwelling catheter does. And again, this is the plasma volume being very stable. Okay. Blood sampling technique was easier method. In vivo measurements still likely to be successful via central line, although we've not pursued that. And blood sampling is available to all patients, inpatient, outpatient, et cetera. Again, we need 3. Current fast method is 3 blood samples. We use the plasma volume indicator to calculate time 0 because we know the volume of the patient and we know the amount of green sample, the small marker injected, and so we get a time 0 that way. Must fully define the early phase to accurately measure GFR. And the third point down there is that observed a greater disparity to the comparator in phase 2 study in normal cohorts. This is why you do phase 2 studies. And we had to resynthesize our compound because of agglomeration. We've done that now, and the new compound is absolutely fantastic. And so we're getting ready for a phase 2B study and have support from the NIH to do that. I'm just going to pass on this for sense of timing, but this is what the new study looks like, drawing 3 samples, calculating a 4th at time 0, getting a readout of GFR, GFR corrected for body surface, vascular leakage, plasma volume, and by knowing the hematocrit blood volume. So the challenge is whether you do this with an external reader or you do it with a blood stick. We have very little data on the effect of edema, ascites, sepsis, and vascular permeability changes. So will it be applicable to the really sick septic patient in your ICU? I don't think any of us can tell you that. Likely, we'll need to do if you're going to do a study and you want to know what the effect of a certain thing is on GFR, you're going to have to do a pre-injury GFR so you have something to compare to. Okay? And then the big question is, do we measure baseline or maximal GFR? I'm leaning toward measuring maximal GFR with a stimulation test to improve sensitivity. So, summary, individual data are critical in AKI. Serum creatinine and eGFR of limited value can be misleading and inappropriately reassuring. Stratifying initial injury and quantifying late response to therapy in AKI are going to be very important, especially if we want to push a therapeutic agent through. Rapid progress is being made in measuring GFR with fluorescent technology. Single and multiple compartment models have their advantages and challenges, and studies in patients with comorbidities will be very important to see how applicable this is going to be to the hospitalized sick patient. Thank you very much.